Welcome to this final lecture of this module, the final one in which I'll introduce new content. That is, we will have one outro lecture where I'll summarize what you've learned in this module and where I'll also give you further resources to study. But let's conclude the content of this module with the relationship between kernels and Gaussian processes. We have already seen that we use kernels to embed our assumptions about how two features relate in a feature space in order to construct the covariance matrices of our Gaussian processes. So there was already some link between kernels and Gaussian processes, but it goes much deeper than that. So let's investigate these deep connections. But before we are able to do that, actually, we have to do a little recap of some very important notions in linear algebra. And also this lecture will be both very technical and also a little hand-wavy because proving all these theorems that you will encounter in this lecture, it's just a lot and very distracting from the high-level ideas that I want to convey. So I'll make sure to provide you with some further resources for you to really dig into the proofs if you're interested. But let's start with little recap. And the first notions I want to recap are eigenvalues and eigenvectors. And for that we need a linear transformation T that maps from a vector space V to itself. V is defined over a field K, and further we let V be any vector apart from the null vector in that vector space capital V. Now we call V an eigenvector of that linear mapping T if and only if TV is a scalar multiple of V. And this means that this evaluation of the linear mapping for that vector V is equal to some scalar lambda times that vector V, where lambda lives in the field over which we define our vector space, capital V. And if V satisfies this equality, then we call V an eigenvector of T. We will also call the scalar lambda an eigenvalue associated with that particular eigenvector V. So let's note that a linear mapping may have multiple such eigenvectors and eigenvalue pairs. So this definition holds for general linear mapping T's, where the dimensionality of the vector space capital V is not specified. But if we assume the dimensionality of V to be finite, then this above requirement is equivalent to this matrix formulation, where we want to have equality between AX, where A is a matrix and X is a vector, and lambda X, where lambda is a scalar and X is a vector. In particular, A is the matrix representation of T, given a basis, and X is the coordinate vector of V. Closely connected to the notions of eigenvalues and eigenvectors, we have the spectral theorem for symmetric or Hermitian matrices. So what does it mean? Suppose we have a square matrix A, which might be complex. And suppose this matrix A is Hermitian. And with Hermitian, we mean that the following property holds. We have that A is equal to the transpose of its complex conjugate. And we may denote this transpose of the complex conjugate is A star. So in the complex realm, we call it Hermitian. For real matrices, this is just standard symmetry, right? Because the complex conjugate of A is just A, and then you have A being equal to A transpose, standard symmetry. And given this setup, we have that there exists an orthonormal basis of V, consisting of eigenvectors of A, where each eigenvalue is real. In particular, we have that A is unitarily diagonalizable. And this means that there exists a unitary matrix U and a diagonal matrix lambda, such that the following equality holds. So A, the linear mapping between vector space V to itself, can be decomposed as a sequence of linear mappings, where the first mapping is U, then we have capital lambda, and then we have U star, the transpose of the complex conjugate of U. And if you evaluate this expression, you have that this is a weighted sum of autoproducts, where UN is the end column of that unitary matrix U, and accordingly U bar transpose is the complex conjugate transpose of that column. So this UN object is n by 1, and this U bar transpose object is 1 by n. And therefore we have an n by n object here, an outer product, and we weight this outer product matrix in the summation with the scalar lambda n. And it turns out that all these lambda n's are the eigenvalues of A, and that the UN are the corresponding eigenvectors to A. So we called this decomposition unitarily diagonalizable. We call it this way because this product, U star, is equal to the identity matrix, the n by n identity matrix. So the columns of U are what's called orthonormal. And also we have that this matrix capital lambda is a diagonal matrix, where the diagonal entries are these n eigenvalues, lambda 1 to lambda n. Now let's have a look at the proper formulation of the lemma we've been abusing in the previous lecture, where we have a symmetric or Hermitian matrix in this complex valued case. And we made use of the following equivalence. If A is positive definite, we had that this mapping is an inner product, right? So you recall this. This is the inner product of two vectors x and y induced by the positive definite matrix A. This is equal to the vector product of y transpose times A in the middle and then times x instead of just y transpose times x. Because the positive definiteness as well as the symmetry or the Hermitian property of A retains all the properties that we require inner products to have. So this is indeed an inner product, and this is equivalent to the positive definiteness property. But what's new to you is that both these statements are equivalent to the following. We have that all eigenvalues of A are strictly positive. In particular, they are real valued. And since these statements are equivalent, showing any of these will be sufficient to show that the others also hold. We're almost done with the recap of fundamental notions of linear algebra and measure theory. And there are just some more definitions that we need. So the first one is the definition of eigenfunctions. We call a function phi that maps from some input space x to the reals an eigenfunction, and a complex valued scalar, lambda, an eigenvalue of the bivariate function k with respect to some measure mu, if the following equality holds. We have that the integral over vectors v in the input space of this expression, the bivariate function k evaluated at positions u and v, times that function phi evaluated at v, is equal to lambda times phi of u. So let's have a sharper look at what this actually means. Similarly to the kernel situation we've encountered before, we fix this argument u. In the second argument, we have all these v's in the input space over which we integrate. And this becomes essentially the mapping that we apply to this vector element. And we want this expression to be a scalar multiple of phi u. So it's just the continuous extension of our definition for the eigenvectors and eigenvalues. And this time phi and lambda are eigenfunction and eigenvalue pairs of that function k with respect to the measure mu, with which we integrate over the input space x. So on a previous slide we had eigenvectors associated with the linear mapping T, and now we have eigenfunctions phi associated with the bivariate function k and the eigenvalue corresponding to that particular eigenfunction. Then we have this definition, a measure mu on a measurable space x sigma x, where x is the input space and sigma x is a valid sigma algebra on that input space. We call this measure mu a finite measure if and only if mu evaluated for that entire input space is finite. So in particular, every probability measure, for example, is a finite measure. And quite naturally, if mu turns out to be a finite measure, then we call the measure space x sigma x mu a finite measure space. So we're almost done with the recap, just two more definitions. I want you to recall the definitions of absolute and uniform convergence. So a real or complex valued series converges absolutely if and only if the evaluated series, where we add all of these absolute values of the individual points of that series, equals L, where L is a real number. Alright, and the definition for uniform convergence is the following. We have the sequence of functions fn that map from some space E to the reals. We call this sequence uniformly convergent on E, on that input space, with limit f. F is a function also mapping from E to the reals, if and only if, for every epsilon greater than 0, there exists a natural number capital N, for which all indices n that are larger than capital N, and all input points x in E, we have the following inequality. So the absolute value between fnx minus fx is smaller than epsilon, right? And this is essentially the distance between two function evaluations for the sequence element fn and the limiting object f. So this is really analogous to what we had for Cauchy sequences, but this is for all input arguments x these two functions could have. So the distance between the evaluations between sequence elements and the limiting object become arbitrarily little. So I know it's just really dry to recap all of these notions, but we are now equipped to digest the full Mercer's theorem, the proper Mercer's theorem. So recall in previous videos we dealt with the simplified version of Mercer's theorem, but here's the full statement. So let's have this finite measure space and a continuous kernel function k that has bivariate input where each argument is from the input space x from our finite measure space. And if k is indeed a continuous kernel, then there exists eigenvalue eigenfunction pairs, lambda I, phi I, with respect to the kernel k and the measure mu, such that this index set I is countable. It may be infinite, but it is countable. We also have that all eigenvalues lambda I are real and non-negative. The eigenfunctions phi I can be made orthonormal, and the following series converges absolutely and uniformly almost everywhere. And this series is the following. It's the iterative construction of our evaluated kernel function, which was the inner product in some reproducing kernel Hilbert space, if you recall. And it's the countable sum. It's not an integral. It's the countable sum over indices in our index set of the following expression. It's the sum of weighted products of evaluated eigenfunctions. So we evaluate phi I for observation u. Then we multiply this with the evaluated eigenfunction phi I for observation v. And then we scale this product by the corresponding eigenvalue corresponding to that particular eigenfunction phi I. And we do this for every index in our index set. And the sum of this will be our kernel. So what have we gained actually? Mercer's theorem tells us that we can decompose a kernel k as a countable sum of eigenvalue eigenfunction expressions. In that regard, it's very similar to linear mappings, matrices, where we had this weighted sum of outer products. And this is indeed very similar. So this intuition might lead you to the question, are kernels infinitely large positive definite matrices? Right? Because recall that we could write Hermitian matrices as the sum of outer products. As I've explained before, A is equal to the finite sum of weighted outer products. And each individual entry of A is defined as the finite sum of weighted entries of these column vectors U. And Mercer's theorem is an analogous result for kernel functions, where the evaluation of a kernel function for observations u and v is equal to the countable sum of scaled eigenfunction products for observations u and v. And recall that this is the formulation of our kernel for the previous lecture. And this suspiciously looks like the individual entries of A, where this formulation of individual entries of A is the result of the spectral decomposition we saw several slides ago. This looks very similar. We just have that this index set may not be finite. So since this is analogous to an individual entry of a matrix A, we may think of a kernel matrix K containing these evaluated kernel functions as being infinitely large, right? We have this kernel matrix K, and each entry is fully specified by the observation pairs u and v, and it's equal to the kernel being evaluated at u and v. And if your input space X from which you draw these u and v's is infinitely large, you have infinitely many observation pairs uv that you could draw. And this kernel matrix K is an infinitely large matrix, infinitely many entries. So in our lecture about the Gaussian processes, as well as the lecture on kernel regression, we had that our kernel matrix was of dimensionality n by n. And this was because we only stored the empirical evaluations for our kernel functions. Empirical in the sense that the input arguments were points that we had available in our training data set. But when defining a kernel function where the observations u and v come from a space of infinitely many elements, then the theoretical kernel matrix, where you store all possible kernel evaluations, that thing is not finite anymore. So now we've seen that Mercer's theorem provides us with an analogous result to the spectral decomposition of matrices. We have that a kernel, which is a bivariate function that is symmetric and positive definite, can be decomposed as a countable sum of eigenfunction products. And given this similarity, we can ask ourselves now, since eigenvectors of a matrix span a space, it's called the eigenspace, do eigenfunctions of a kernel also span a space? And if so, what is that space? Let me give you the answer to these questions. It's yes, indeed. The eigenfunctions of a kernel span a space, and that space is, surprise, the reproducing kernel Hilbert space H, which is induced by the kernel. We will have a closer look at that in a few slides. It's called the Mercer representation of the reproducing Kernel-Hilbert space. But before that, let me show you a really interesting relation between Gaussian processes and the reproducing Kernel-Hilbert spaces. So first, let's observe that the Gaussian posterior mean is a least squares estimate. So what do I mean with this? We have this posterior conditional density, and this is the density of our estimations given the true labels. Right, so this is the estimation model, which is drawn from a Gaussian process, and this is conditioned on the true labels we have available. And via Bayes' theorem, we have that this conditional density is equal to this expression. So this is the likelihood of our true labels given our predictions times the prior distribution over our prediction models, and we divide that by the marginal over the labels. And if we insert the corresponding densities into these expressions, we have that we arrive at this density. So the likelihood y given our prediction model is a multivariate Gaussian density parameterized by this expectation and this covariance matrix. And this expectation is our prediction vector y hat, right? We apply this prediction model to the full data set, and we have this covariance matrix sigma squared times the identity. And this is something that we've seen before in the Gaussian process lecture. So this shouldn't be surprising to you. Also, the prior distribution over our prediction models happens to be a Gaussian process because we want to draw these prediction models from the Gaussian process. And this Gaussian process is parameterized by two parameters. The first one is the mean prediction model, M, and we have the entries of the covariance matrix, which is parameterized by a kernel. And this mean model may be zero-centered. So on expectation, you generate the null prediction, which is just a vector of zeros. And finally, you divide by a multivariate Gaussian density, where the random variable is your true label vector y. The expectation of that is the mean prediction on your full data set from that Gaussian process. The covariance matrix of this multivariate Gaussian is the empirical kernel matrix of our full data set, plus some regularization covariance matrix, sigma squared times the identity. And this is just the result of marginalizing over all possible prediction models that are drawn from the prior distribution. So similar to the Bayesian linear regression scenario we had in the previous lecture, this is now independent of the prediction models. We have integrated over the prediction models, and therefore this posterior is proportional to the likelihood times the prior distribution. And now you can solve this entire expression. It involves a lot of algebra. It's not fun. So let me just give you the full parameterization of this Gaussian process, this posterior Gaussian process. So again, the random variable is our prediction model, and the expectation is this expression. The entries of our covariance matrix associated with that Gaussian process is this expression. So the expectation of this posterior Gaussian process is this mean prediction model plus this bit. And we use it to adjust our initial assumption about the prediction model given the data we have available. So here we have again the inverse of the empirical covariance matrix plus some regularization matrix, and we multiply this from the right with the true labels minus the predictions generated by this mean model, the assumption that we had in our prior distribution. So this is essentially the prediction error generated by our prior model. And from the left, we multiply this row of a kernel matrix. So we compare the observation for which we want to generate a prediction with every entry in our dataset X. And similarly, the entries of the covariance matrix of this posterior Gaussian process are updated entries to the prior Gaussian process that we started with. So this bit defines the entries of the covariance matrix of the prior Gaussian process. And from that, we subtract the information that we gain by having a data set. So again, this is something that you've seen before in the Gaussian process lecture. We have this empirical covariance matrix. We add a regularization covariance matrix. We take the inverse. This is the information gained by our empirical data. And we kind of squash it into the right dimensionality. This needs to be a scalar by multiplying this row vector, this kernel row vector from the left, and this kernel column vector from the right. And since all of these quantities are positive definite, we have that this entire product, which is a scalar, will be a positive scalar. And also a kernel is positive, so from that positive entry, we subtract something positive again, which effectively subtracts uncertainty from the entries in our covariance matrix of the posterior Gaussian process. So for this slide, I copied the first bit of the previous slide. And I want to convince you again that the Gaussian posterior mean is a least squares estimate. And for that, let's find the expectation of our prediction vector. So this is the model drawn from the Gaussian process, the posterior Gaussian process, applied to the dataset X. This is our prediction vector y hat. And this expectation is over the posterior conditional density, which happens to be the posterior Gaussian process I showed you on the previous slide. And since this posterior Gaussian process is a Gaussian density, we have that the expectation of that will be the maximum point of the density. So this expectation is equal to the argmax of the posterior density. The argmax in that case is the prediction vector y hat that maximizes this posterior Gaussian process density. Now, maximizing a probability density is equivalent to minimizing the negative log of that density. And it turns out, if you write it out, it's not fun. So here the work has already been done for you. This is equivalent to minimizing the following squared error. So we are now looking for the augmented predictions that minimize this expression. So it's some constant times the squared magnitude of the difference between the true labels and our predictions. So we've seen that numerous times now. It's the squared magnitude of the epsilon vector plus some constant times the squared magnitude of the posterior predictions and the prior predictions. So we have this prior prediction model M, which was the expected model prior to having observed any data. This was encoded in our prior distribution. And essentially this serves as a regularization term again, because if we set this expectation to the zero model, then we only have the squared magnitude of our predictions, which is similar to what we've seen before. So we penalize large predictions. But if we embed some assumption into our prior Gaussian process, then this will be a non-negative prediction. And any deviation from that initial expectation, the prior expectation, will be penalized. Larger deviations will be penalized more heavily. Smaller deviations will be penalized less so. And you might ask yourself, okay, what is this magnitude? It could be many magnitudes, but it's a very specific one. So it's almost the squared L2 norm, where you have vector products. You multiply this vector with this one, but again in the middle. So this is similar to what we had in the previous lecture. In the middle, you have a positive definite matrix, and in this case, it's the empirical kernel matrix, the inverse of that. And since this inverse is positive definite, we have that this expression is a valid inner product. And since we have the same vector on the left and on the right, this inner product turns into the squared magnitude of that vector. So this magnitude is almost like the squared L2 norm, but it is parameterized by the inverse of the empirical kernel matrix. So now we've seen something really interesting. If we do Bayesian linear regression, which is a probabilistic approach to finding the best fit to our data, it returns an expectation that is equivalent to the minimizer in the least squared scenario, which we dealt with in the first half of this module. So it's really nice to see that the Gaussian processes basically do what we tried to do analytically in the first half of this module, when we were minimizing the squared error. But the connection goes even deeper. I want to make the claim that the RKHS, the reproducing kernel Hilbert space induced by the kernels, is the space of possible posterior mean functions. So for that to see, let's recall that a reproducing kernel Hilbert space H is just the space of linear combinations of kernel functions. So any element in that reproducing kernel Hilbert space, so these are functions, are just linear combinations of partially evaluated kernel functions. So admittedly, this notation is a little sloppy, but I'm sure you recall this construction of the reproducing kernel Hilbert space. So now I want to convince you of this claim that I made before. So let's find the posterior Gaussian process, like we did before, where our prior is zero-centered. So this mean model M is just zero, and the likelihood is just what you would expect. If we then do the Bayesian update and arrive at the posterior, we arrive at this expectation. Let's call it mu to differentiate it from the prior expectation M. And if M is set to 0, as in our assumption here, you will see that this expectation will be this expression. So you can go back 2 slides and you will see that this is the expectation that we arrive at when doing the Bayesian update. This is the expectation of the posterior Gaussian process. And if we just define this bit to be called alpha, then we have that this expectation is a finite sum of entries of alpha times the entries of this row of a kernel matrix. And lo and behold, this is a linear combination of kernel functions. And therefore this posterior mean function, the expectation of our posterior Gaussian process, is an element of the reproducing kernel Hilbert space. And in fact, this form is so general that we conclude that the reproducing kernel Hilbert space H is the collection of possible posterior mean functions in the Bayesian Gaussian process learning scenario. And this is already a really deep insight, so let that sink in. So now that we've looked at the first argument of the posterior Gaussian process, which is the expectation, let's now have a look at the posterior variance. So this theorem is a little more complicated. I will not prove it, but you can look it up. We assume again that our prediction model is drawn from the Gaussian process, the prior, which is zero-centered. So again, m is equal to 0 without loss of generality. And our observations are noise-free. So this is a simplifying assumption that we investigated in the Gaussian process lecture. Of course, it also generalizes to noisy observations, but it's easier to investigate the noise-free case. Then we have the Gaussian process posterior variance, so the expected squared error, so this expression. So it's the expectation over the posterior density of the squared difference between the realization of our random variable, the prediction model, and the expectation of our posterior Gaussian process, right? So this is just the definition of the variance. And we found this, so individual entries of this covariance object are the entries of the prior covariance matrix minus some information that we gain from having a data set. So I hope you recall this. This was on a previous slide. So it's the variance of the posterior Gaussian process. And this theorem states that the variance of the posterior Gaussian process is a worst case bound on the divergence between our expectation and an RKHS element of bounded norm. So what does it mean? We have that the variance is equal to the supremum of the squared deviation from the expectation of our Gaussian process, the posterior Gaussian process, and elements of the reproducing kernel Hilbert space H, where the norm of these elements of the Hilbert space is normed, so smaller or equal than 1. So the more you think about it, the more obvious it becomes. So you want to quantify the squared deviation between your expectation and some elements in the reproducing kernel Hilbert space. Because again, on the previous slide, we had that the reproducing kernel Hilbert space contains all possible posterior mean functions. So it makes sense to compare these two quantities. So now we come to the promised Mercer representation of the reproducing kernel Hilbert spaces. And this theorem states that if we have a bounded and closed metric space X, a continuous kernel K, and a measure mu is a finite measure on X, then if we let this collection phi I, lambda I, be the pairs of eigenfunctions and eigenvalues of K with respect to mu, then the reproducing kernel Hilbert space H can be written as follows. So previously we had that the reproducing kernel Hilbert space is the space of linear combinations of kernel functions. And now we will see that elements in the reproducing kernel Hilbert space, so these are functions, are equal to countable sums of scaled eigenfunctions, scaled by the square root of the eigenvalue associated with that particular eigenfunction, and also scaled by this alpha I. Because the reproducing kernel Hilbert space is the linear combination of kernel functions, and therefore any element of H is a linear combination of kernels, they might be weighted differently, and these weights alpha I correspond to the weighting of the kernels. And the sum of the square root of the eigenvalues times the eigenfunctions suffice to define the partially evaluated kernel functions, so that there's one free argument. So by summing up, you arrive at a kernel function that you can scale, and therefore you have this mapping that lives in the reproducing kernel Hilbert space. But we need to restrict this space, because otherwise our inner product will not be defined, so let's do it. We need the elements of the reproducing kernel Hilbert space to be of bounded norm. So that means if we take the squared norm of any element of the reproducing kernel Hilbert space, it should be finite, and we will define the norm as follows. It's just the sum of squared coefficients alpha I. And from that formulation of the squared magnitude of an element of the reproducing kernel Hilbert space, we arrive at this inner product formulation. So the inner product of psi and xi is defined as the sum of products of coefficients, where the coefficients alpha I are just the coefficients here for this function psi, and the coefficients beta I are the coefficients for that function xi. So let's give a proof sketch of the Mercer representation of the reproducing kernel Hilbert space. And to show this, we have to first show the RKHS property 1, which is that for every observation u in our input space, we have that the partially evaluated kernel, partially evaluated for that observation u, is an element of the reproducing kernel Hilbert space H. So in the Mercer representation, we have a form of the individual entries, and we require them to have finite norm. So let's see whether this works out. Of course it does. So we have for every observation in our input space that the partially evaluated kernel for observation u is equal to the sum over indices of this bit here and this bit. So let's have a look. So the first bit is square root of the eigenvalue times the evaluated eigenfunction evaluated for the observation u, and this specifies the first half of our kernel function. And the second half needs to be free. So we have this evaluated bit times the square root of the eigenvalue again, times the eigenfunction, which now is not evaluated. And this now becomes a scalar because it's evaluated, and we can define the scalar to be alpha I. And this is exactly the shape of the elements of the reproducing kernel bit space. So if we now can show that every partially evaluated kernel is of bounded norm, then we have that RKHS 1 holds. So let's have a look. The squared norm of the partially evaluated kernel is equal to the inner product of that kernel with itself. And we defined this inner product to be the product of coefficients at the front. And since these are the same entries, we have that we square this coefficient. And then we sum all the squares of alpha i's up. So let's do that. We have alpha I here. And if we square that, we have the sum of eigenvalues associated with an eigenfunction phi I times the evaluated eigenfunction phi I, evaluated for the observation u, to the power of 2. And now if you look sharply at it, you will see that this is the fully evaluated kernel, where both arguments are occupied with the observation u. And this is indeed finite, so we conclude that for every observation in our input space, we have that the partially evaluated kernel function for that observation is in that reproducing kernel bit space H. Now for RKHS2, we need to show that the reproducing property holds. And for that, we want to show that this inner product is equal to this expression. So we have the inner product of an element of the RKHS. Let's call it psi, with the partially evaluated kernel for the observation u. This should equal the evaluated function psi for observation u. And let's see that this indeed works out. Recall the definition of the inner product for that reproducing kernel bit space. It's the sum of products of coefficients at the front of these arguments. And for this function psi, it's called alpha I. And for the partially evaluated kernel, we have this coefficient. So for RKHS1, we called it alpha I, but now it's beta I guess. So we have that this is the inner product of these two functions. But it turns out that this is also the representation we have for elements in our reproducing kernel bit space. Also, this function is evaluated, right? So we have the sum over indices of some coefficient times the square root of an eigenvalue of an eigenfunction. We multiply this with the eigenfunction, and this eigenfunction happens to be evaluated for observation u. We have that this is indeed equal to the function psi evaluated for observation u. And this indeed shows the reproducing property of the reproducing kernel bit space H. And now let's finally employ a lemma which states that RKHSs are unique. And with that we have shown that the Mercer representation is indeed equivalent to the explicit construction that we had 2 lectures ago when we were building the reproducing kernel bit space H as a linear combination of kernel functions. So now we've investigated the mean functions of a posterior Gaussian process, the variance, and the Mercer representation of a reproducing kernel bit space. But what about the draws from a posterior Gaussian process? Are they elements of the reproducing kernel bit space? Let's find out. So we have this theorem which states, again with all the setup, let X be a bounded and closed metric space, let K be a continuous kernel, mu be a finite measure whose support is X, let this be the collection of eigenfunction eigenvalue pairs, and further we have this collection of random variables Ci, which we draw from a standard Gaussian density, and with that we have that the expectation of the product of Ci and Cj is equal to the Kronecker delta. So it's 1 if the indices coincide and 0 otherwise. And with all that setup, we have that functions of the following form are draws from a Gaussian process, which is zero-centered. It's the sum over indices of this product. So these first coefficients are the draws from the standard normal Gaussian density. We multiply this with the square root of the eigenvalue associated with an eigenfunction phi I, and multiply this coefficient with that eigenfunction phi I. And again, we have that this is a draw from a Gaussian process that is zero-centered, and its covariance matrix is parameterized by this kernel function. And this representation looks like the identity of the elements of the reproducing kernel bit space in the Mercer representation. But even though this looks so similar, let's not get confused. This theorem states that such a construction is a random draw from a Gaussian process. But now let's find out whether such a function psi is indeed an element of the reproducing kernel bit space. Spoiler, it will not be, actually. And the reason for that is, if that inner set I is infinite, and we draw such a function as we defined on the previous slide from that Gaussian process, then this implies almost surely that psi is not an element of the reproducing kernel bit space. And this is because the expectation of the squared magnitude of that function is equal to the expectation of the sum of squared coefficients zi. And by linearity, you can push this expectation inside the summation, and you have that we sum up all these expectations of squared zi's, and this expectation will be 1 because the indices coincide in this product. And then we sum up infinitely many 1s, and this will diverge. So on expectation, the squared magnitude of a random draw from a Gaussian process is not bounded. And if we were to allow such elements to exist in the reproducing kernel bit space, we wouldn't have a proper inner product on that space. Therefore, we must conclude that Gaussian process samples are not in the RKHS. Let that settle. We have that the RKHS is the space of all possible mean posterior functions of Gaussian processes. But the draws, and these draws might deviate from that expectation, the draws themselves are not elements of the reproducing kernel bit space. Not generally, at least. But it would be odd, I think, if there was no relation between the draws from a Gaussian process and the reproducing kernel bit space induced by the kernel. And this will lead us to the final theorem of this module. So let H be an RKHS. And further, we have some number theta that is strictly larger than 0, but smaller or equal than 1. Now we construct a new set, which we will call H to the power of theta. And it's defined as such. So recall that for the Mercer representation of the reproducing kernel bit space, we had that elements of this space were sums of products, where the product consisted of some coefficient, the square root of some eigenvalue, and some eigenfunction corresponding to that eigenvalue. And now we change this bit. So the square root of an eigenvalue, lambda I, is equal to lambda I to the power of 1 over 2, right? And what we now do is we multiply this 1 over 2 with that value theta. And the rest we keep the same. So the squared magnitude of any function in that space is also just the squared coefficient at the front, the sum of squared alpha i's. And this also needs to be finite for an element to live in that space. Now this final theorem states that if the sum of eigenvalues lambda I to the power of 1 minus theta is finite, then we have almost surely that a draw from a Gaussian process lives in that space. So this draw will generally not live in the reproducing kernel Hilbert space H, but it will live in that larger space, H to the power of theta. So we conclude Gaussian process samples are not in the RKHS, but they are elements of a larger space with a similar construction as the reproducing kernel Hilbert space. So I hope you can find some appreciation for these results. It's been terrific. I had so much fun doing that, and we will conclude with one final outro lecture where I will summarize what you've learned on a high level, and I also have a surprise for you. So see you next time.